Hello and welcome. This is Schrodinger's cat explained. So I'm going to start you off with a question. If a tree falls and no one is around to hear it, will it make a sound? You've probably heard this question dozens of times, and usually just as a fun philosophical question meant to make you think. However, as you're going to see, it takes on a new relevance in the face of quantum physics. Today, I'm going to tell you a story. Story about a quantum physicist. This man's name is Erwin Schrödinger, and in 1935, he came up with a thought experiment to show other scientists how current theories of quantum physics contradicted common sense. In Schrödinger's experiment, you put a cat in a box, one that is completely impervious to outside observation. In that box, you've got a sample of a radioactive element, a Geiger counter, a hammer, and a vial of toxic gas. Now, let's say that this radioactive element has a 50% chance of decaying and a 50% chance of not decaying within a span of time. If the element decays, the Geiger counter will trigger the hammer to smash the vial of toxic gas, killing the cat. But there is also the chance that the element will not decay, leaving the vial unsmashed and the cat still alive. This means that we have two scenarios, both equally possible, one in which the cat is dead and one in which it is not dead. According to the accepted laws of quantum physics at the time, such as the Copenhagen interpretation, the atom for all practical purposes is both there and not there. I'll touch on why people thought this in just a moment. But for now, let's think about the implications of this for the cat. If the atom has both decayed and not decayed, then the cat should be both alive and dead. And no, I don't mean like a zombie cat. We have to assume that the cat is in both states until the box is opened. But the simple act of observing the result will make the outcome definitely one or the other. And we have no way of knowing what went on while the box was shut. Could the cat have been in both states until we observed it? Well, that sort of question is exactly what Schrödinger was trying to make us think about. Now it's time to look at some of the science behind it. Are you ready? Schrödinger's cat is largely based on a concept called superposition. The basic premise is that there's a range of places an electron can be, and a variety of states that it can theoretically occupy at any given moment. And there's a completely random chance it will be in any one of those states. Therefore, we have to consider it in all states at the same time. However, superposition can't be observed, because just as with the cat, as soon as we observe the electron, we will know for sure which position it is occupying. And I know what you're saying. That's not physically possible, because there's only one electron. How can it possibly be in multiple places at the same time? And I know, it does sound pretty ridiculous. But there is some physical evidence of this theory. And this is what I call the dual slit experiment. Now in this setup, we have a surface with two slits in it, which we will shoot a stream of electrons toward. A surface behind the two slits will record where the electrons hit if they make it through one of the slits. We would expect particles to behave a little like this, just as if we were to shoot marbles through the slits instead of electrons. You can see that they line up, for the most part, behind the two slits. On the other hand, wouldn't we expect a wave to act like this? You can see that the waves go through the slits at the same time, radiating out from that point and interfering with one another. In this pattern, some parts cancel each other out, and others amplify each other. But you can see a distinctive pattern of where electrons hit the back surface most intensely, lining up with the amplified points on the intersecting waves. Now, say we took this double slit experiment and fired one electron at a time. You would expect to see something like this. It's the same pattern as a particle, right? But really, it's going to look something like this. Contrary to the particle pattern that we might have expected, this, in fact, matches up with the interference pattern created by the two separate waves clashing with each other. But how can this be? Well, to show you how it works, I'm going to try covering one slit at a time and shooting electrons through. Now the other slit. As you can see, all the electrons lined up behind the slits, just like particles would. So, why do we have a wave pattern when we shoot them one at a time? That sort of motion would require one electron to go through both slits simultaneously, interfering with itself to cause the pattern. But say we were to watch the electron go through, to see which slot it really goes through. Scientists have found that when the particles are observed or measured, the superposition collapses, or ceases to be, and the electron will go through just one slit. Why is this? Some scientists say that it's because measuring anything will interfere with the particles. Some even say it's due to our own perception. Either way, the bottom line is that we don't know what quantum particles are doing behind our backs. Now, let's circle back to Schrodinger. If the cat is able to observe the decay in the Schrodinger experiment, then shouldn't the superposition have already collapsed? Well, not quite. For the cat, there is no superposition. It will either be alive or dead. But we, the scientists, don't have a way of knowing what's happening inside the box, so for us, the superposition does still exist. Up until we open the box and see what's happening for ourselves. What Schrodinger was trying to tell us with his experiment was not how particles acted, but how our ideas of quantum physics would really mesh with the Newtonian world. Our worldview tells us that a cat cannot possibly be alive and dead at the same time. So does that mean that an atom being in two states at once is impossible? To tell the truth, we don't know.